Good morning, friends. Today we are going to see one of the applications of the linked list, that is the polynomial representation. And we'll see in this video the addition of the two polynomials. So polynomial can be represented using the linked list and to perform the operations on them using the linked list. One of the advantages that we are having for the linked representation of the polynomial is it is not going to waste a lot of the memory, because when we are implementing the polynomial representation using the arrays, there are so many terms that are having the zero coefficient. We have to allocate the memory for them. To overcome the disadvantage of the wastage of the memory, we are using the linked representation. We represent in the linked list only the terms that are present in the polynomial. When we consider a polynomial, the polynomial can be represented as an expression p of x that is present in the form of ax power n plus bx power n minus 1 so on jx plus k. K is the constant term that we are having. N is called the power of the or degree of the polynomial, and a, b, c so on j, k are the constants that we are having. So when we are representing the polynomial is composed of the different terms that are consisting of two things. One is the exponent, another one is the coefficient. This we are also calling as a power. And when we are considering this particular polynomial, we can represent the constants as the positive numbers or the negative numbers. But generally the polynomial is consisting of non-negative integer called as a n, which we are calling as a degree of the polynomial. The representation that we are having for the polynomial is the polynomial is represented in this particular manner. As an example, when we are considering the 4x cube plus 6x square plus 10x plus 6, the 4 and the 3 are the terms of this particular node. So the node is represented as 4 and 3. And the next term that we are having is 6 is the coefficient and the 2 is the power that we are having, 6, 2. And 10 x power 1 we are representing. This we are writing as a 6 into x power 0, so 6, 0. When we are representing the polynomial, the main things that we have to remember is the sign of the coefficient is not stored separately. It is present with the coefficient itself, because integer can hold both the positive numbers and the negative numbers. And exponent is a positive number that we are having. And the additional terms, that is the same degree terms, will not be present multiple times. Only once we will be having the power. Suppose if the power 2 has been taken, only one term will be there with the power. And the storage allocation for each term in the polynomial must be done in ascending order only. That means we are considering the terms in this particular fashion, either this particular ascending order or in the descending order that we can consider. So generally we are representing here in the form of descending order only. Now, as an example, when we are considering the first number 5x square plus 4x plus 2, and the second number as 5x power 1 plus 5x power 0. When we are adding these things, the output that we are getting is 5x square plus 9x plus 7. And similarly, when we are considering the another example, 5x cube plus 4x square plus 2x power 0, and we are adding the second number, this is the output that we are getting. That is 5x cube plus 4x square plus 5x plus 7x power 0. That is 7. These are the examples of the polynomials and what we are adding. Now if you see the representation that we are considering, the first polynomial is considered as a list 1. That is the first polynomial, 5x square plus 4x plus 2x power 0. And the second list that we are having, 5x plus 5x power 0, that is 5. When we are adding, we will be adding the similar power numbers and we are getting the output as 5x square plus 9x plus 7. So when we are considering this particular thing, the node structure that we are having is, first thing we are having a coefficient, and the second one is power or exponent that we are having, and the address of the next node that we are having. The node structure that we can represent is struct node, int coefficient, and int exponent, and the address of the next term is represented as struct node star next. So that means normal single linked list is used for representing this particular polynomial. So when we are adding the polynomial, mainly we have to consider the 4 different types of the cases. Here I have taken the two polynomials. The first polynomial is represented by the P1 and the second polynomial is represented by P2. And the resultant polynomial is represented by using the P3. That means the start of the first polynomial is P1, the start of the second polynomial is P2, and the start of the third polynomial is P3. P1, P2, P3 represents the three polynomials. So initially we will consider the first case. When we want to add the two polynomials, the P1 is now pointing to the 8x power 11 and the second polynomial P2 is pointing to 7x power 11. Here in this case, the two exponents are same. The first polynomial exponent is 11, second polynomial exponent is 11. In such cases, we are adding the two coefficients, that is the polynomial 1 coefficient 8 and the polynomial 2 coefficient 7. The resultant polynomial is consisting of the term 15x power 11. So the third polynomial is consisting of 15x power 11. How this came? Whenever the P1 exponent is equivalent to the P2 exponent, we are creating a term with the coefficient as P1 coefficient plus P2 coefficient 15, and the exponent that we are considering is any exponent is same, we can represent this one. That is, the case one is P1 of exponent is equivalent to the P2 of exponent. Then the thing that we are doing is P3 of coefficient is coming as P1 of coefficient plus P2 of coefficient, and P3 of exponent can be anything, P1 of exponent or P2 of exponent. Then these two terms were over, then P1 goes to the next term and P2 goes to the next term. So these are the activities that we are performing whenever the P1 exponent is equivalent to the P2 exponent. The resultant term is consisting of P1 coefficient plus P2 coefficient as a coefficient and P1 exponent as exponent. This is the case 1. And we will see the case 2. So case 2 is the thing that we are having, that is P1 exponent is 3 and P2 exponent is 4. So P1 exponent is less than P2 exponent. In such case, whatever the term that we are having the highest exponent, that will be placed as a result for us. So whenever this type of case is coming here, we are considering this as 5x power 4 because the 4 power term is not present. We are considering the P1 exponent 3 is less than P2 exponent 4. So whatever the highest exponent is there, this term will be placed into the result. So that's why P3 of coefficient is P2 of coefficient and P3 of exponent is P2 of exponent. Because only this term has been added, P2 is going to the next term, that is P2 is going to the P2 of next. So the three operations that we are performing are, whenever the P1 of exponent is less than P2 of exponent, in such cases, we are performing the activity as P3 of coefficient is equivalent to P2 of coefficient and P3 of exponent is equivalent to the P2 of exponent. Because this term is over, P2 goes to the next one, that is P2 of next. The third case that we are considering is P1 of exponent is greater than P2 of exponent. In this type of case, whichever the term that is highest, that will be placed. Now the P1 term is highest, that's why P3 of coefficient is equivalent to the P1 of coefficient and P3 of exponent is equivalent to the P1 of exponent. Because this term has been added, P1 goes to the P1 of next. So P1 goes to the P1 of next. These are the three operations that we are performing whenever P1 of exponent is greater than P2 of exponent. Then the fourth case, if any one polynomial was over and there were another terms that are left out in this one. As an example, consider that after performing the activities, the P1 reached null. That is, polynomial 1 is over. Then in such type of cases, whatever the terms that are left out in P2 has to be added to the third polynomial. Here 3x power 0 is there that we are adding. So suppose in some cases P2 will be over, then whatever the terms that are left out in the P1, we have to add to this one. So the fourth case is, if one polynomial is completed, the terms in the other polynomial has to be added to the resultant. Okay. Now we'll see the program for polynomial addition. In this polynomial addition, we are taking the node structure. The node structure is consisting of exponent and coefficient, and it is also containing the pointer to the next term. These are the three things that we are having for the node structure, and we are taking three polynomials. The first polynomial is represented by the start 1, and the second polynomial is represented by the start 2, and the third polynomial is represented by the start 3. For the three polynomials, we have taken the three starts. All the three starts are pointing to the null, because all these polynomials initially contains only the null values. Now if we see the display function, so the display function from the highest term to the lowest term that we are displaying until the last term we have to display. This is the display operation of the single linked list. The pointer is starting at start. While the pointer is not equivalent to null, we are representing the pointer of coefficient and the pointer of exponent. After representing one term, we are going to the next term. Like this, until the pointer is becoming the null, we are performing these two activities. Whenever the pointer is becoming the null, we are coming out of the display function. Now these are the two functions that we are having. Add node is the function that is used to create every term in the resultant polynomial. Create function is the function that we are using for creating the polynomials initially, that is P1 polynomial and P2 polynomial. At first we will see the add node. So whenever we want to add a node, in the example if you see, we are adding these nodes at the end of the linked list only. So that's why every polynomial term has to be added to the end only. For that particular purpose, if you see this particular example, so after these three terms, the 3x square has been added at the end only. That means it is nothing but insertion at the end of the linked list. The resultant polynomial, every term we are adding at the end of the single linked list only. So that's why this add node is the function that we are using, is the insertion at the end. If you see that one, we are creating the new node, and whatever the coefficient and the exponent are there, we are placing that particular coefficient and exponent. N is the exponent and C is the coefficient that we are representing. For the new node of exponent, we are placing N, and for the new node of the coefficient, we are placing the C that we are getting, and the new node of next is pointing to the null. If the resultant polynomial is not there, this will become the first term. Otherwise, we are adding at the end. Already we know this particular code. The pointer is starting at start until the end of the linked list. The pointer is incremented, and at the end we are adding these things. This already we know that one. And creating the polynomial. This is also the same activity that we are performing. This is the activity in which we are creating the polynomial with the multiple terms. So we are performing this activity until you tell yes. So initially I am considering coefficient and exponent. Suppose 8x power 11 that we are giving. 8 and 11 I will be giving. So I am creating a node for that one. So do you want to continue? Yes. Like this we are adding terms to this particular polynomial until option is given as yes. Once the option is given no, the polynomial will be terminated and I am displaying the polynomial. Now we will see the function for execution, the addition of the polynomial. The addition of the polynomial is taking the start 1, start 2 and start 3 as input. Pointer 1 points to the first polynomial, pointer 2 points to the start of the second polynomial. This operation we are performing until the two polynomials are not equivalent to null. This is the case 1. If the polynomial 1 exponent is equivalent to the polynomial 2 exponent, I am creating the sum of the polynomial 1 coefficient and polynomial 2 coefficient, and that is added as a new term for coefficient. And polynomial 1 exponent is placed into this particular start 3. And P1, P2 points to the next terms. And if P1 exponent is less than P2 exponent, whichever greater we have to add, that is P2 exponent has to be added and P2 coefficient has been added to the start 3. And P2 goes to the next term. And if P1 exponent is greater than P2 exponent, P1 term is greater than, so we are adding that particular term to the third polynomial. And it is going to the next one. And if the P1 is not equivalent to, P1 is equivalent to null, the first polynomial is over, then the terms that are present in the second polynomial are added to the resultant, that is polynomial 2 exponent and polynomial 2 coefficient. If polynomial 2 is over, the terms that are left out in the first polynomial are being placed into the resultant. and we are creating